So in the last class we saw, we did not go into the second part of the details, but we defined the measure and we saw an upper bound. And if you complete the lower bound, then you will get that this simple polynomial, which is VBP polynomial, right, iterated matrix multiplication, this has homogeneous depth 4 complexity optimal. So this is theta square root d, d raised to theta square root d, because you can implement it in this much size, and we have shown that nothing better can be done. And this method was generalized slightly to other models and also for other fields. So this was further generalized to some model called sigma gamma sigma pi. So this basically refers to, this will take too much of notation, something like this. So this gamma is basically referring to, again, product of sparse polynomials, but their transcendence, so their algebraic rank is bounded by square root d. So instead of their number, so their number may be anything, may be arbitrary, but their algebraic rank is small. So this actually refers to the algebraic rank of the factors. Yeah, gamma square root d refers to algebraic rank of the factors being square root d. It doesn't talk about Fanon, it talks about the algebraic rank. So this was done in a paper by Pandey, Sinha Babu and myself, 16. So this is more algebraic. So yeah, I mean, this measure has been extended in several ways, the measure of shifted partials. Any questions? Okay, so now what we will do is just quickly go through an interesting point that was made by some authors in 2017, which refers to the potential limitation of these techniques. So the question is whether you can come up with a creative measure. So first come up with a vector space and then come up with then look at the rank of that vector space, and using this strategy can you show VP different from VNP, right? So this is the ultimate goal. So can this be done by just being more creative about the vector space and about the measure? So since it will be a vector space based measure, it is fair to say that we are looking at determinant, right? Because rank of vector space is essentially determinant of some vectors. So our lower bound proof they were all rank based. So which is also determinant based. And to be in particular, what we were doing was the following. So we use a determinant based polynomial M that takes as input the coefficient vector of f. So the determinant will be of what? It will be applied on the coefficient vector of the polynomial which you want to study, right? Because that is all you can compute determinant of. So the vector space basically. So for example, if you look at the space of partial derivatives, right? So that is also exactly of this type, that it is basically playing with the coefficients, with the coefficient vector of f, and then it extracts other vectors from this, and then it looks at the determinant of all these vectors which have been extracted, right? So it's basically we can say that this determinant based polynomial m is acting on the coefficient vector of f. Yes.
I mean, the determinant you just tell about the whether it's full rank or not, right? I mean, like that rank, how do you build one?
Minor. Rank is obtained by minor, which is also a determinant. So to show that f is in a complexity class D but not in C, right? This is what we want to show when we are interested in explicit in a polynomial that is both explicit and hard. So it is explicit for D and it is hard for C, right? So it's in D minus C. This is what we want to show. That's the target in all these lower bound proofs. So to show this for algebraic complexity classes C and D, what is done? So what is done is three things. So first we show that for any polynomial in C, mg is 0, right? So this is the upper bound part of our strategy. So when we show that this sigma pi root square root d, sigma pi square root d shifted partials on this is small, right? That when we show that upper bound, we are basically looking at some determinant m, and we are saying that all these polynomials g that can be computed by these models, m vanishes. So that's the upper bound. That's the first thing. Second is you show that f violates this. Right, that's the lower bound part. So f you have to then design creatively. So we looked at determinant, for example, or iterated matrix multiplication polynomial. That's f. So once we have shown 1 and 2, what do you get? This means that f is not in C, right? Clearly this implies that f is not in C. And third is which basically follows in the previous proofs by construction, that f is in D. That is the explicitness. So we want these three properties, and then we have a explicit lower bound, right? So the observation made by Forbes, Spilka and Folk in 17. So their observation was that if your complexity class C is complicated enough, right, in the worst case think of VP, So then VP we know has pretty complicated polynomials. Right? Even determinant is there and many other things are there whose coefficient vectors are supposed to be pretty complicated. So if you believe that there are coefficient vectors which on which a big determinant will not vanish, or in other words there are coefficient vectors that will be non-roots of determinant, right, then property 1 can never be satisfied. It cannot be true that for every g in C mg vanishes. If you believe that your coefficient vector of g for some g in VP is hard enough or is complicated enough, then determinant will not be able to kill it, right. So property 1 cannot be satisfied. So it's a conditional thing. If there exists a g such that coefficient vector of g is a non-root of determinant, if this is assumed, it's a conjecture, then it's a hypothesis. So if you assume this hypothesis, then f naught in C cannot be shown. By rank based measures. Simply because property 1 is false. So since property, if you won't be able to show even property 1 if C is a complicated class. So hence this whole strategy you won't be able to make it work. Is that clear? So assuming that there are these polynomials in VP whose coefficient vectors are complicated, by which we mean determinant doesn't vanish, right, then these measures will always be limited. You cannot separate VP from VNP. So this C here is, think of it as think of C as VP and D as VNP, right. This is the motivating example. But then VP is not really a simple complexity class. It's a class that has all types of difficult looking polynomials. I mean, they happen to be in VP, but those proofs are always non-trivial. And the polynomials have exponentially many monomials.
You are saying कि for this class VP, there is no such characterization as given in 1, not known.
It is unlikely for determinant if M is determinant. So whatever determinant based polynomial you will design as M, it is expected that there will be a G in VP whose coefficient vector will keep it non-zero. So that is also called there is a G that hits determinant. So G will hit determinant. I mean, determinant is a non-zero polynomial, and if you look at the coefficients that appear in G and use them to evaluate determinant, determinant will be non-zero. I mean, that is expected because G has all sorts of coefficients. There is no reason why determinant will vanish at this point. Yeah, so this is the core of their paper, but The paper has many other things, and it formalizes this and also implements many known hitting sets in their formulation. So that will be covered by Abhibhav at a later date. Any questions? But this is the code. This is the reason why people may believe that these measures will not generalize. So what do you think will generalize? If these measures don't generalize, then does it mean you can never prove VP different from VNP?
Different user.
We always can different PIT.
Yeah, that is where I will go next. But here, one loophole that you can employ is, I mean, in the measure, do not keep your measure to be strictly a polynomial of the coefficient vector. So, for example, you can make it a non-polynomial by saying that I will also go into the bits of the coefficients. So, whether the ith bit of the jth coefficient is 1. So, if you ask these if you force bit operations or these checks with bit operations, that will not be a polynomial, that will not be a determinant polynomial, because it is looking at not just the variable x1, but actually when you substitute the coefficient in x1, it is going inside the bits or the string of x1, right. So then these arguments will not hold anymore, right. So you might talk about inequalities, whether the coefficient is greater than 0 or whether a bit is 1 or 0. So those things are not simply a question of determinant. Yeah, so all sorts of things you can do. That is not covered in these limitations. But we were not doing that in the previous proofs. As Prateek wants, that brings us to polynomial identity testing.
But is there any approach for constructing measure related to codes? Because in local decoding kind of thing we pick bits.
Sure.
There are approaches.
Whether there are approaches, I don't know. But you can try. Prove a new lower bound.
I thought if there is.
No, not currently, but it's not ruled out. Feel welcome. So PIT is the question of given a circuit, you have to say yes or no depending on whether the circuit is identically 0. Right. So the word identity here just means whether your circuit is encoding an identity. Right. So that is what this word identity means. So identity example is x plus y, x minus y, minus x square minus y square. Right. So this may be your circuit, and this is identically 0. Although if you look at the intermediate computations, nothing is 0, but it's at the very end that you get. At the very end of the formula, you will see that everything will cancel out. So that is the challenge, that it is about representation. It is not about the polynomial, that is, because the polynomial is just 0. So which is why this question is not covered under standard algebra or standard algebraic geometry, because it is really about the representation. So in this case, for example, this is a formula. So I have given you a formula where everything is non-zero, but in the end of the calculation you see 0. Monomials cancel out. Right. So it's a question inherently about the representation. So PIT is the algorithmic problem. Given an algebraic circuit, let me not say algebraic, let me say given an arithmetic circuit, C x bar over a ring. So coefficients come from a ring R of constants. Test whether C is identically 0. Okay, that is the question. It's a decision problem. So when we say given a circuit, arithmetic circuit, we mean that you can see all the gates and you can see wires and you can see the constants on the wires. So as an algorithmic problem, it will make sense to also count the bit representation, right? So when there is a constant, it should be represented in bits. So that is one thing we can assume here, that input is in bits. So in algebraic complexity, we don't worry about the constants. Constants can be anything. But when you ask for an algorithmic problem, then you have to talk about what is the input that will be put on the Turing machine input tape, and that could only be bits. And in terms of those number of bits, what is the time complexity, right? So that time complexity then is defined and space is also defined. So we want an algorithm that has time complexity polynomial in the size of the circuit. Right, so size actually is now bit size. Is this clear? That is the problem definition. It's an algorithmic problem. And since it's an algorithmic problem, it will not make sense to use constants like square root 2 or e or pi. So we will just use constants, either they are elements from a finite field or they are elements from the integer ring, right? So we can just use the simplest possible constant. In fact, since you have addition multiplication gates, you can start with just 0, 1, minus 1, and then using this you can build everything else, all the other constants. So you can also assume constants to be just of 3 types. So we'll focus on the case of R. So the ring will be a field for us. So the field will either be the field of rationals or the finite fields. Now, there are innumerable other fields which we are ignoring, but it will not matter. I mean, algorithmic problem will always reduce to one of these 2 types. Okay, so this is really enough to solve. So what is the representation size for constants in FQ? Yeah, so any element in a finite field you can write in just log of the field size, many bits. And the representation for rationals or integers will of course be in bits, and it can be arbitrarily big. So that how big it is, that will be counted in the input. No, that is fine, but what the size of A will be the value of A log, that many bits. So it can be arbitrary. And yeah, so what is the status of this problem? How do you solve it practically? So that we have seen in the early assignments, right? This Schwarz-Zippel lemma. So Schwarz-Zippel, and there are other authors. So this lemma, I mean the lemma you saw in the assignment will tell you that PIT is in co-RP, which is definitely in BPP, but one-sided error. Okay, so it is in randomized polynomial time with one-sided error. The error is on which side? When the circuit is 0, obviously you will say that circuit is 0, but when the circuit is non-zero, then you may be fooled, right? So it's on non-zero side, so it's in co-RP.
That error problem kind of captures BPP.
Two-sided. BPP is two-sided.
Yeah, or PIT is one-sided,
Okay.
and that carbonate Baglia says it should be randomized in BPP. So one-sided problem kind of captures with some condition.
Yes, that is happening because of PRGs. Yeah, so I think in that lemma about zeros of a polynomial, you might not have seen all the cases, so we'll just go through the cases without going into the details of each. So you are given a circuit Cx bar of size S.
What's the status of the problem if you consider rings and not fields? You can't apply Schwarzschild and stuff anymore, right?
Wasn't this also a part of that question?
Okay, what's the domain? So what if it's not a domain?
Yeah, so that is, so all these things you are supposed to do in that.
No, the
Yes.
question didn't say anything like that.
No?
No, no.
Didn't it ask for when R is not a field, what happens?
I mean,
You could have, and then you were able to say that for domain you can just.
Right.
Schwarzschild doesn't work, right? But what about the problem itself?
Yeah, there is a lot to say.
Okay.
Let's not say it now,
Okay.
because you have to talk about the structure of the ring and all.
Yeah, if it is not field, then which kind of ring that is?
Yeah, I mean, you look at the whether it contains a field and then how far is it from the field. So depending on that, you can simulate Schwarzschild.
If it's a UFD, it's a domain, then it's no longer interesting.
I mean, it's not a field, it's a ring.
But in any domain, it's Schwarzschild. The only interesting case when it's not a domain.
Yeah, so
Even there, the harder. I mean, we can pinpoint what are the harder rings. It's not that for non-domains the problem is always hard. It's only hard when the non-domain is very far away from a field.
So if it's like a direct product of many domains, then it'll be harder because you'll have many.
Yeah, for example. Okay, so basically we have to. The thing is that the algorithm is different for the two fields, two families of fields. So for finite field, it is a bit different than when the field is the field of rationals. There is a slight difference, so which is why I am doing this proof, because there are some technicalities involved. I mean, idea of course is just that you pick a random point and evaluate your circuit C. But then there are some technical issues in proving getting the probabilistic, showing that this is a valid probabilistic algorithm.
Q may not be large enough. That is.
Yeah, FQ may be a small field, that is one problem, and on the side of rationals, the problem will be that at a random point when you evaluate the circuit, the number may become far too big than you can store. So for example, if you have the degree of the circuit is 2 raised to s, then x raised to 2 raised to s, if you substitute x equal to 2 there, it will immediately output 2 raised to 2 raised to s, which you will never be able to store anywhere. So yeah, all kinds of technical issues are there, so we'll see how that is done. So because of circuit having size s, so we are in this case of FQ. Good. You know that the degree of C is bounded by certainly s to the s. Yeah, it cannot exceed that. In every level you are multiplying s things, so degree cannot go beyond s to the s, but this is an exponential degree. So we actually need to apply that lemma of Schwarz-Zippel. We'll need that size of the field is greater than s to the s, slightly more than s to the s, right? But then that may not be true. The field may be just having two elements. What do you do then? Yeah, then you go to a field extension. So what will be the degree of the field extension? It will be the log of this size. So that will be Pauli in S. So for this, if needed, go to a field extension.
Okay. I was thinking what happens if your polynomial is Frobenius x raised to p minus x. So that also can be taken by this.
Of degree, degree will not be needed more than s log s or something. So O tilde s. So it is not, the degree of the field extension is not too large. So do you know how to go to a field extension of a finite field in randomized polynomial time?
So, you can explain
You can complete, I mean, it will be isomorphic. I mean, you can look at it as a vector space and you can compute that efficiently.
No, I am saying how do you find the field extension of required size? Right, so you have to, yeah, you basically guess or randomly pick a polynomial of degree this much, O tilde s. And if you are lucky, it will be reducible, and that defines a field extension.
For that only randomized polynomial.
Well, you have to show that. You have to show why is picking a random polynomial good enough.
there's a lot of
Yeah,
videos with
that
that.
is also.
How do you know? How do you know that?
And not only you want to count irreducible polynomials.
It's not very hard to count the number of irreducible polynomials, right?
No, nothing is hard for me. But what is the,
The product of
how do you do that?
the product of all the irreducible polynomials, you know what that will be. So if you're only
Yeah.
considering products of, and if you're only considering irreducible polynomials of product of degree d, then you can just sort of divide the degree of the extension that contains
Right.
of the product of all the irreducible.
So it is possible to do like that, but I will not go into those details. So let me just leave this as an exercise. Finding a field
But
extension.
that is also only randomized polynomial. That's
Yeah.
not determined.
Well, so the simple thing is randomized polynomial time, but there is also a deterministic way to do it. So there is a paper by Adelman Lenstra that does it in deterministic polytime. So also there is a Adelman Lenstra paper. That can be invoked directly. It's from the 80s.
Deterministic polynomial.
Yeah, so
Serious in that course, in the computational.
yeah, no, this needs Gaussian sums and exponential sums, so we don't do that in the course, but it can be done. So this actually, if going to a big enough field extension is not a problem at all, it can be done in deterministic polynomial time. Okay, this is the bottom line to remember. More than that, you do as an exercise. Yeah, so we then assume basically without loss of generality that our field is quite big. Okay, so the circuit that we are given over a finite field, that field is exponentially big in terms of the size. And then things are easy. So now for this case, the algorithm is simply the PIT algorithm. It is simply an evaluation. It's a random evaluation of the circuit. So pick a subset of the field of size 2 times s to the s. Since it's a finite field, you can pick the whole field as s. Just take s to be f in the extension, and pick a random point a1 dot dot an from s to the n. So this random process will not be very expensive, because how many random bits would you need? This is n times log of s, log of the size of big S, right? And the size of big S is smallest to the smallest, so it is just O tilde S again, O tilde ns, right? So this just requires O tilde n times S coins. Right, so you just need to flip these many coins and unbiased coins, and it's fine. So you have now this point A bar. So evaluate C at A bar, check whether it is 0, the value is 0. If it is 0, then you will output that C was 0. That's the output. If C is not 0, well, then you have a certificate of the non-zeroness of C. Right, so this is correct, and this may or may not be correct, because you answered too soon. Right, I mean, this A bar may be a root of C, it may be a 0 of C. So that is what you have shown. You have done an analysis in a previous assignment. So it has been proved before that if C is not identically 0, then the probability that C at a random A bar from this big enough S to the n is non-zero is quite high. Okay, so this is 1 minus degree of C over the size of the set S. Degree of C by size of S is around half, so this is greater than half. So this output 0, you will be correct with probability 51%, for example, and then you can repeat this and you can boost it to arbitrarily close to 1. You can boost it simply because this is one-sided error, so it will be easy for you to see that just repeating this and taking a majority vote brings the probability, success probability, close to 1. And yeah, so that makes it a valid probabilistic algorithm, and time complexity is clearly polytime. So clearly C A bar can be computed in time poly in S and log of F. Right, so the input was the circuit of size S and field F, which is a finite field. So in the input size, this is a polynomial time algorithm, and probability is bounded, so it's a probabilistic, or it's a randomized polytime algorithm. Any questions? Right, so the other case is now F equal to Q. So in this case, C A bar could be as large as 2 raised to S in value. right? Because just look at x to the 2 to the s and plug in x equal to 2. So this is now beyond our storage capacity. So any ideas? How will you modify this green algorithm?
Big prime.
Exactly. So you reduce modulo primes. Yeah, so for that you should be willing to believe that there are enough primes around. So once you believe that, then if you need, let's say, s square bit primes, right, you just randomly pick a number of s square bits and then do a primality test. So then it's a prime with high probability and you go mod that prime. So this number, for example, 2 raised to 2 raised to s modulo p, where p is s square bits, right? This computation you can do in the circuit when you are multiplying and adding. You can do that arithmetic mod p at every point, so the size will never, the bit size will never blow up, because every time you are dividing and taking the remainder, right? So remainder mod p will only be p minus 1 at most. So your answer will be s square bits instead of 2 raised to s bits.
So if you randomly pick a number, then that is not good, right? It's like log and
But the primality testing is one side correct. So it's fine.
Yeah, so you have to be willing to believe that there are enough primes. So
Take a prime which is exponential and bit size is poly. So take a range of exponential poles.
So you can't test all of that.
the number of primes could be
You
small.
can't test all of it. You don't have enough time.
No.
But then the primality testing is one side.
he is not asking about primality test.
So I'm saying that
It's asking
when
how
you
you
think
pick
about, primes, like if you randomly pick primes, then the probability that the thing is a prime is very low.
It's one by poly. It's one by poly.
It's log and
It's
if you do the prime number.
it's log. But it's like log. It's poly s, right? It's one by poly s.
So it is for s square bits, it is 1 over s square.
Your range is exponential.
So you just repeat. So your error probability is,
1 by poly.
your success probability is 1 over s square, but then you can boost it. You can boost the success probability.
You can make 1 by poly.
The whole day you keep picking primes, and then the probability will be high that you hit a prime in some hour. And when you hit, then the primality test will also tell you with confidence, very close to 1, that it's a prime. Or you can use AKS, which will tell with 100%. So either way. Okay. So that is the idea. You reduce C A bar. Well, don't reduce in the end, because then it will be too late. You have to compute modulo p. So compute C A bar. So mod p is inside. C A bar mod p. So do this computation. Mod p arithmetic for a random p. For a random prime p of bit size around s square, let's say, and this you can randomly pick. Sure. The probability analysis will not do. This is again an assignment. You have to use the prime number theorem or prove it. So that I am skipping. Abhibhav at least has seen in a class.
You don't need the tight error bounds. You just need the weakest error bounds. But that's what half a semester.
So you are claiming that they can do this exercise?
No, I didn't say that. It's like an NP, right? You can see your proof and verify it quickly.
Okay. Sure.
You take n1 and n2. N2 is 4 times n1. N1 is exponential is ns. In that range, n1, 20 is big prime.
No. What is the probability that it's a prime?
Yeah, so
That you have to prove.
because the range is exponential, probability is 1 by poly s. And then
why-
you can-
Why? Why is that?
Why 1 over poly s?
That you have to prove.
Because you are picking prime in range n1 and n2.
Okay.
Both are exponential in s. So So prime is exponential, bit size is poly.
Sure.
What if there's only
Now n2 is 4.
What if in that range there is no prime?
No, if you only have
0
one
prime.
prime,
Everything is composite.
He's speaking like twice. Between every n1 and 2n1 there is.
But what is the proof?
There are proofs.
Yeah. So those things I am leaving as an exercise.
even that's not enough, right? But just have a prime between N1 and 2
But
N1.
yeah,
you
you
still have prime
don't need
far
to
away.
need that proof n1 and 2.
Even that's not
You are just taking n1 and some
So-
poly times n1.
So compute the error.
In that range you can use just prime over 4. So you can get exponential number of times.
So compute the error probability of this process, which will give you a prime. But then one minor complication is that this prime may actually divide CA bar. Right? CA bar is a large number, but the random prime that you picked after such hard work of one day turns out to be a factor of CA bar, and so CA bar is 0 mod P. Right? So that error probability also you have to estimate. So you have to estimate that so the errors can be well, P is not prime, or P is a prime but then P divides CA bar, and A bar itself may be a root. Right, so there are 3 types of errors and you have to estimate each of them. So CA bar being 0, that we have estimated before. Prime P dividing CA bar, this you will rule out, or you will estimate the probability by saying that not too many primes can divide CA bar, because it can be as big as something like S to the S to the S, and how many prime factors will it have? At most S to the S. So these S to the S are the bad primes. You remove them, still S square bit primes are way too many. So this is a very minuscule set of bad primes. So you will not pick them with extremely high probability. They will be missed, and P is not prime, that you, or P being a prime, for that you need prime number theorem. Yeah, so these things I leave as an exercise. So if none of these errors happen, then you have a certificate of C being non-zero, right? With high probability. Okay, so that finishes. So thus in all cases PIT has a randomized poly time algorithm. And there is no mistake on identities. So the algorithm by nature will never make a mistake if C was 0, because it is simply evaluating. In some ring it is evaluating, so if it was 0 it will remain 0, but when it's non-zero then it makes mistakes. Any questions? So one property of this, I mean, so this is a practical algorithm. In practice it will run extremely fast, and the other nice property it has is that it doesn't care about the circuit. So it takes the circuit as a black box.
You can't do the modular again.
Yeah, so just ask the black box to do arithmetic in this ring.
Okay.
So you have to request the black box, but then black box will not tell you how it is implementing that.
But what is the well, okay. How does the time code mixture work? Because In general, you can't ask a black. I mean,
Why not?
even how your polynomial is being computed by some arbitrary process. Assuming that you can't do that.
It's addition multiplication. There is no arbitrary process. It is not a neural network.
But now you're looking at the black box. You can't look at the black box.
No, we are not looking. We are requesting the black box to do arithmetic mod p.
Black box will have input as also.
So suppose you are the black box, right?
It's like a gray box. What is
So,
the black
so
box?
you will not show me the wires and the edges and the nodes. You will do the computation and you will just tell me the answer.
You can do the computation with a lot of ways. So
I think black
Because
box
every step in the black box is defined mod p. So you can make this request. It's a valid request.
but so the black box circuit that comes, it counts as over Q, right? But I mean,
Right,
circuit
yes.
is even over Q. Then like it also takes input a prime as well, where it
Yeah, that's
allows you to input the prime.
So that will be a formal way, yes, to define
Or we
the
can
black
take
box.
the
Yes.
Black box and then again a black box.
Yeah. So the black box will not only compute a polynomial with rational coefficients but also modulo primes. So you give the prime. So nowhere in the analysis did we use anything about the circuit looking in a particular way. That is what black box means.
But is there any difference in like any setting where it matters whether you consider the constants as part of your input size or not? I mean, in one case you can get a polynomial time argument, but the other case you can't. Because
No. So it will only matter when the coefficients are integral because they can be arbitrarily huge. So when you are leaving it to the black box, so how will the black box compute mod p, a number that is triply exponentially large? That
I can't tell you what the number is.
yeah, but so if that is being done by the black box, then you
I mean, instead of doing this whole thing, instead of requesting the black box to do the computation mod p, you could just ask the black box to tell you whether it's 0 or not. Whether
Sure.
the evaluation is 0 or not. And then you don't even have to, and then the bit size doesn't matter, right? Like you can have an algorithm which is independent of the size of the constant.
sure. Yeah, but when you are talking about circuit being given to you, then you have to talk about input size.
That's a white box, right?
Yeah, then you have to talk about input size. So then you know that the coefficients are only exponentially large. They cannot be triply exponentially large.
So are there algorithms that like, look at the coefficients that, like don't work if
Sure, I mean no, I'm not saying they will not work, but there are algorithms and it is also conceivable that you can use the constants and the wiring.
So what is given in black box model? Size is given.
Yeah, in black box model, all you know is the circuit size.
Only size is given.
Yeah.
And the number of variables.
Sure, I mean that is a property of the box. Yeah. I mean we usually think of number of variables also in the size. So S is the size bound, and there are S variables, and there will be a single output. No, in this the theorem was not talking about black box at all. Theorem was just saying that the algorithmic problem of PIT is in co-RP. That's all. There is no black box here. So that's follow-up observation that in the above algorithm, the specifics of the circuit C are not used. So it only requires size bound. So only the size bound and field, underlying field. So such an algorithm is called a black box identity test or black box PIT. Okay, so it was presented as a white box algorithm, but actually it can also be used as a black box algorithm because it never cared about the circuit anyways. It's just evaluation based. It only needs to evaluate C. Now, this is where the older questions which you are asking apply. So, evaluate C where? So, either, so black box should allow you to evaluate either in an extension of the ring or in a reduction of the ring. So, evaluate C either in extension K of your field or R mod P. Okay, so evaluation should be allowed in either extension or reduction. So, yeah, it is true that when we talk about black box, these are the assumptions, that the black box will allow us to go either to a bigger field or reduce mod P when possible. It may also be other, you can also say reduce modulo. So, you substitute, for example, x1 equal to t and say that I want the answer mod t square. I mean, those other ideals can also be used, but usually they will all reduce to these two cases. Nothing stronger happens by, I mean, except these. Okay, so yeah, so if this is confusing, if this model is confusing, there is a much better way to talk about black box PIT, which will be by removing the circuit C from the picture. So now we will not even look at C. We will not look at the black box. Our question will just be a design question, designing a set of points. Okay, without looking at C at all. So you can think of that as a non-adaptive algorithm. So you are evaluating the black box at different points, but your next result doesn't depend on the previous result, or next evaluation point doesn't depend on the previous results. So we call that set hitting set for a family C of circuits, let's say n variate of size S. A hitting set H is a subset of f to the n it's a poly S sized set of points such that if a circuit C is given in the family C, which is non-zero, then what? What should the hitting set do? It should have a non-root of C. So then there exists an alpha bar in the hitting set such that C alpha bar is non-zero. Okay, so we say that the set H hits the circuit family C, because whenever you pick a non-zero circuit in the family, there is a non-root in H, right? And you should notice that the circuit family has, even when you fix the size S and N, usually there will be infinitely many circuits, right, simply because the field is infinite. So for these infinitely many circuits, there is a small heating set, right? So at this point you should wonder whether these powerful things even exist, because infinitely many polynomials will have infinitely many roots, and why are they away from H, right? H is a small set, so there is really no reason at this point. So colloquially we will say that H hits C. Yeah, so now it's a design question without even looking at a circuit. So the question is just you will be given, let's say, this number S in unary. On the Turing machine, on the tape, S will be written in unary, so 1 to the S is input, and you have to output in the output tape of the Turing machine a set of points, H. Okay, and the question is how fast can you do this?
Tell you which type, I mean, as stated not, but usually they tell you which type of family, right? Design and things for this class of polynomials.
That is contained in C. That is a description of C, but the Turing machine question or the algorithmic question is just given 1 to the S, output a set of points. And this algorithm should be as efficient as possible. Right? And you don't even know whether this H even exists at this point. Forget about the efficiency. Sure, you can think of C as kind of VP, just any circuit is given to you, or you can think of it as depth 4, or you can think of it as depth 3 or depth 2, right? So these are the example settings we are interested in. Okay, so what about the existence question? Say I remove this condition of poly S sized, then can you at least show that there is a finite sized H that will hit all these infinitely many circuits? Yeah, so that is Schwarz-Zippel. So another corollary of Schwarz-Zippel is that there is a finite H. So hitting sets exist, finite hitting sets exist, finite and inefficient hitting sets exist. So let's just state that lemma and then we leave. So let S be of size S to the 3S and C be the family of size S circuits, n variate over I don't need a finite field, I think just F over F. So S is a large enough set and C is a family of all circuits size S. Then a random A bar in S to the n hits C. So this is just a reformulation of Schwarz-Zippel, right? If you take your ground set, sorry. Yeah, sure. You can say that. Yeah. I mean, this is just no. This is not weaker.
I mean, Schwarz-Zippel will give you the probability of A hitting C.
No, but by random A bar hitting, the probability is hidden here. Yeah. So this is Schwarz-Zippel. So what is the hitting set that this is giving? S to the n. So S to the n is your hitting set because I mean hitting set just needed one element A bar, and here almost everything in S to the n will hit your circuit. Actually, no.
Why would a random A bar?
It's like S to the Sn because it's like degree to degree.
I see. No, I wanted to say something else actually.
C could be the family of circuits that vanish at A.
Hmm.
That means but it depends on what C is. Not just the degree, but the structure of C.
Okay, let me change it a bit.
Vanishes over the
What if
set.
since if it is non-zero, then you will have
Okay, let me. Then for all C in the family, a random A bar hits the circuit.
Suppose C is VP and DS, you can always interpret when a polynomial that passes through it. No single point can hit C. No single point can hit your circuit. C is
No, there is also a formulation with single point, but let me specify the circuit here. So, for any non-zero circuit C in the family, there will random A bar will be able to hit it. This is exactly Schwarz-Zippel. If you want the previous result, a single point that hits every circuit in the family, then I will have to talk about finite field here. Because if the field was finite, let us say of size q, then the number of circuits is only q raised to s. So the circuits are actually few. In Schwarz-Zippel, you do a union bound, so you will get q raised to s times s raised to s divided by s to the 3s. Yeah, so then actually you can also do that. Yeah, but so these are simple implications from Schwarz-Zippel, but they still don't tell you whether there is a small heating set. These heating sets well, actually the 1 point thing was fine. Yeah, the heating set of size 1 exists. That was okay. But it doesn't tell you anything about efficiency. How will you produce this heating set? Yeah, so let me stop now. So next time we will continue the study of heating sets.